In this video, we are going to talk about contours, and we will see that contours are important because integrals of complex valued functions of a complex variable, and that's what's different between this and the previous integrals we did, where we had real variables. Now we're dealing with complex variables, are defined on curves in the complex plane rather than just on intervals of the real line, and we'll be looking at classes of curves that are adequate for the study of such integrals. The picture that you will see in this video is here. It's a comparison of real valued functions with real variables. So when you integrate a real variable from a to b, there's only one path from a to b. It goes from a through all these other real numbers till eventually you get to b. The problem with functions with complex variables when you have complex variables, it takes the entire plane to represent one point, whereas here all you needed was the x-axis. So here you have the point AB in the complex plane, and you have the point B in the complex plane. Now, when you want to integrate from point A to point B, now here, instead of just a line, one possibility, you have many ways to get from point A to B. So here's one possibility, the straight line, or maybe you're going to do a curve of some sort, an indirect curve, or maybe you'll do half a circle or something. But the idea is that now, when you integrate, there are many possible paths, and that's why we define integrals on curves. And these integrals on curves are exactly the line integrals you worked with in vector calculus. So we will talk about contours or arcs, which is a set of points in the complex plane z equals xy, where x is a function of t and y is a function of t, and we often imagine t as time, and that our function x of t tells us where the x-coordinate is at time t, and y of t tells us where the y-coordinate is at time t. So in effect, as t progresses from a to b, we see a curve being drawn in the complex plane, and the curve drawn is given to us by x of t, y of t. We also have simple arcs if the curve does not cross itself, and we have a simple closed curve or Jordan curve when it is simple except for the fact that z of b equals z of a. In other words, the endpoint is the same as the starting point. And one other note, often the geometric nature of a particular arc suggests a different notation than the parameter t. So t is a nice parameter because we can think of it as time, but often, like for a circle, we think of parameterizing by theta, or for a line, we might parameterize by x or y, or we can parameterize by t. Unlike in vector calc, when our line integrals had all kinds of curves, in this class generally you'll be working with straight lines and with circles, like so many circles. But anyway, we will look at a straight line, and the circles we will look at are based on z equals e to the I theta, and we'll do some variations of that, including z equals z naught plus r e to the I theta, where z naught moves the center of the circle to z naught, and this capital R increases our radius or decreases our radius to big R. And another note, the parametric representation used for any given arc C is not unique, and we will do an example where we parameterize one path using two different ways. And now that we know about arcs and simple closed curves, we can talk about a contour, and a contour is a piecewise smooth arc. And an arc consists of a finite number of smooth arcs joined end to end, and we will see an example of that. And then also we talk about the exterior and interior of a curve, of a closed curve, which is intuitive. So inside the circle would be the interior, outside the circle would be the exterior. So that was our overview, and now we're ready to get into the details. In our last video, we looked at complex valued functions of a real variable, and we saw that derivative and integrals could be done in a very natural way. And in particular, once we have our complex function, we could break it down into a real and imaginary portion. Both u and v are both real valued function, but v is then multiplied by I. And once we break it down, then for the derivative, we could just take the derivative of u of t and v of t, multiply v of t by I, and then add it to u of t. So it's a very natural way of doing this. Similarly, for for definite integrals of complex value functions of a real variable t, if w was our complex function, we could break it down into a real part and an imaginary part. And by imaginary, I mean this v of t was a real function, but then we would multiply it by I. So when we take the integral of w of t, we can then break it down into taking the integral of u of t plus I v of t. And at this point, v of t and u of t, we're taking integrals of real functions, which we know how to do. In this video, we're going to start looking at complex valued functions of complex variables. So no longer real variables, but complex variables. And that adds some complexity, no pun intended. To start by showing you the comparison of complex value functions of real variables versus complex values of complex variables, I'm going to look at real valued functions with real variables because I can then graph my f of x, y, and I'll compare that with functions of complex variables, and then I'll tell you why this still applies to complex valued functions of real variables. When we started in first year calculus, we had our variable x, and then y was dependent on x, so f of x is equal to y. And then we would integrate this function, so we could plot our f of x equals y on this graph. And when we would integrate with respect to x, our variable, our independent variable, and we would integrate as x went from values from a to b along the real number line. And to get from a to b, we would just go from a all through all these real numbers in between until we finally got to b. Let's compare that to functions with complex variables. Now we're going to compare that to functions with complex variables. Now if we want to integrate our function f, which takes a complex variable z, so z, a complex number, has to be mapped in the two-dimensional coordinate plane because z has an x-coordinate and a y-coordinate. If we want to integrate z from a to b now a is a two-dimensional coordinate. In other words, a is equal to x plus I y1, and b is equal to x2 plus I y2. So then when we integrate from a to b, there's not just one path we can take. Certainly we can take this straight line path, but we can also take maybe a curved path, or we could take some totally randomly strange path to go from a to b. So again, over here, when our domain is a real number, to get from a to b, there's only one path. It's the straight line through all these real numbers between a and b. Here, because a and b now are in two dimensions, we can have all kinds of different paths. And our integral, the value of our integral, is going to depend on the path we choose. And you might recall from vector calculus, we had path integrals and line integrals. So this is exactly that topic here, except that now we call them contours. And if you don't remember vector calc, that's okay because we're going to, or if you don't remember line integrals from vector calc, that's okay because we are going to review it. And also for the study of complex analysis, there are only certain types of paths that we typically deal with. But essentially here we have the idea of a contour, or the importance of them. So integrals of complex valued functions of a complex variable. Remember, now we're doing complex variables, so there are multiple paths between two complex variables. They're defined on curves in the complex plane, right? So our integrals are now defined on curves, rather than just intervals on the real line, which are these boring lines. We will be looking at classes of curves that are adequate for the study of such integrals. In other words, we don't have to have quite the breadth that we need to have in vector calc, but we'll need to look at important classes of curves. And that's exactly what this video is about. We'll start by introducing the contours, and then in the next video, we will look at contour integrals. Next, we're going to look at some definitions. An arc is a set of points z equals xy in the complex plane, which x, this coordinate x, is equal to some function x of t. And this coordinate y is some function y of t, for t goes from a to b, where x and t and y of t are continuous functions of the real parameter t. So it's a parameterized path. As an example, let's consider z equals t comma t squared. That is, x of t, our x coordinate, is equal to t, and our y coordinate is equal to t squared. We can make this table of t versus x of t and y of t. So when t is equal to 0, x is equal to t, which is just 0, and y is equal to t squared, which is 0. When t is equal to 1, x is equal to 1, y is equal to 1. When t is equal to 2, x is equal to 2, and y is equal to 4. We have 3, and then -1, -2, we have -2, and then we have 4. So you will recognize this as this parabola here. And especially when our variable is t, we often think of t as time, and over time, our parameterization will trace out a path. So if we go back in time at -2, then our point is -2, 4. So we're here. As time progresses, we'll be going down our path, and at -1, as t is at -1, we're at point -1, 1. As we keep going, as time progresses, and when we get to 0, we hit the 0, 0 point. Time then becomes positive. As time gets to 1, we're at point 1, 1. So again, it's the idea is that t is time, and then our parameterization, t squared, traces out a path in time. Or you can think at any time, let's say 3, you can figure out where this point is going to be. At 3, it's going to be at the point 39. An alternate notation is to describe the point z of t, where z of t is equal to x of t plus I y of t. So I wrote that in here. Z of t is equal to x of t plus I y of t. So you can see I wrote that for each point. And in the complex plane, let's just look at 2, 2, for example. That should be at 2 plus 4i, which is exactly this point here. I chose to parameterize this with t because I like thinking of this, in time, that we're tracing out this curve. But another way this could have been parameterized is that your x coordinate is just equal to whatever x is equal to, and then y is equal to x squared. And this makes it more explicit that the relationship between y and x is that y equals x squared, which is of course the parabola you're familiar with. The arc is a simple arc, or also called a Jordan arc, if it does not cross itself. That is, C is simple if z of t1 does not equal z of t2 when t1 does not equal to z2. So in other words, if we're coming over here in time and we're tracing out this arc, and then as time progresses, at some point we loop back around and cross ourselves. It's not bad to loop around this way, but if we loop back over here and cross ourselves, so remember, this is not t, this is x versus y, but in some time t we come back and cross, then we're no longer a simple or Jordan arc. This one would be fine because it does not cross itself. An arc is a simple closed curve or Jordan curve, so the idea is a curve, not just an arc, but a curve. When the arc is simple, except for the fact that z of b equals z of a, so there's a starting point and an ending point. Such a curve is positively oriented when it is in a counterclockwise direction. Counterclockwise, in other words, in increasing radians. So here's an example. I'm going to start, and actually remember, this is an x coordinate and y coordinate for a complex number. I don't have in this graph, I can't show time in this two-dimensional graph, which is why I'm drawing this in real time, because the time I'm using now is when I'm drawing it. Anyway, so here we are at time equals 0, and I'm going to start following my path, and it can take any number of things. It's not going to cross itself until the path is at the very end and it's done, and it's going to come back to my starting point, and that's the idea of a closed curve. And there's a note: the geometric nature of a particular arc often suggests a different notation for the parameter t. So it's convenient to think of curves being parameterized in time by t, but for example here, we often think of a being drawn and it's parameterized by theta. So let's take this example. Z equals e to the I theta for theta going between 0 and 2 pi, and we'll see that this draws out a curve as we follow theta going from 0 to 2 pi. Here I've rewritten e to the I theta using Euler's identity. The radius is 1, so I have cosine of theta plus I sine theta. So now I can make a chart of theta versus x and y. And x is my cosine theta, or 1 times cosine theta. My y is 1 times sine theta. So when theta is equal to 0, I get cosine equal to 1, 0. So theta will start over here at 1, 0. And I'll just mark that in black. As theta progresses, now instead of thinking of time progressing, we're thinking of theta progressing at pi over 4, which is approximately here. We're going to have x equals square root of 2 over 2 and y equals square root of 2. So we have this point. So we have theta progressing through time. Eventually we reach this point over here. The next we have pi over 3, which is 1/2, and 3 pi over 2, so theta keeps progressing. And then as theta crosses pi over 2, which is straight up on the y-axis, we're going to have x equal to 0 and y equal to 1. This should have been a 1 here. So we come and we meet this, and you can see that we keep going as theta is equal to pi radians. Then we're going to be at -1 and 0. Coming down over here, as theta progresses to 3 pi over 2, so that's 3 pi over 2 radians, we get x equals 0 and y equals -1. And then finally, as theta comes around to 2 pi, we come back to x equals 1 and y equals 0. So this is our circle, which actually looks a little lopsided, but so maybe this looks a little better. And we're thinking of the circle as being drawn as theta progresses, and you can see as theta progresses, we're going in this counterclockwise direction, and we also see that it's a simple closed curve because we start where we begin. So I've written these two facts down. It's a simple closed curve because z of 0, our start of our path, is equal to z of 2 pi, the end of our path. And as I said, as theta progresses, we go around in the counterclockwise direction, so I can denote that with this little arrow. Now that we have the definition, we're going to look at 4 more examples. Our next example is going to be the polygonal, I didn't even know this was a word, line defined by z equals x plus ix for x between 0 and 1, and z equals x plus I for x between 1 and 2. So in this case, our variable z is parameterized by the variable x. In other words, x is kind of what z depends on. The independent variable, z is the dependent variable. So when x is equal to 0, we're on this line, x between 0 and 1, and z is going to be equal to 0. When x is equal to 1/2, I had to do fractions, z is equal to 1/2 plus 1/2 I. When x is equal to 3/4, we have 3/4 but 3/4 I. And when x is equal to 1, it could be either, but we see both are equal to 1 plus I. And this is also 1 plus I. Now we're in this range, x between 1 and 2. When x is equal to 1.5, then we have 1.5 plus I. And when x is equal to 2, we have 2 plus I. And now I can graph my curve. I have my point 0, 0 here. This is the first point in time, z is equal to 0. The second point is equal to 1/2, 1/2. My next point in the xy plane is equal to 3/4, 3/4. And then my next point in the xy plane is 1, 1. As I go on in time, I have x equals 3/2. I have 1/2, and then 1 and 1/2, which is here, and then plus I, so I have plus 1, and then at 2, I have 2 plus I, so my y coordinate is equal to 1. So you can see I have this line that goes up, and you can kind of see that this is where, because x equals y, so I have my x equals y line, and then here, as x increases between 1 and 2, I have the line where y is equal to 1. So this is my curve, and you can see it progresses. You can think of it as progressing in time, going this way, or as x progresses, I guess it's not so much time, but as x progresses, my curve progresses. And just looking at this also, I pulled the z equals x plus ix. Another way you can express that is that z is equal to xx. In other words, y is equal to x. And that, to me, makes it more clear that this is parameterizing the line y equals x. Also, if you wanted to parameterize by t, this would be t, and this would also be t. Here, if we had this, we can also parameterize z equals x plus I, as z equals x, and then there's a 1 in front of the I, so y is equal to 1. And this also makes it more clear that this is the line y equals 1. And then a couple of more variations on this line. If I had z equals x, and then y is equal to x plus 2, this would be the line y equals x plus 2. And also, I could have expressed this as x plus I, x plus 2, right? Just saying that y equals x plus 2. And if I wanted the line for x equals 2, I set x equals 2, and then y just varies, or you could put this equal to t. So whatever y value is, you're saying that x is equal to 2. Just some other parameterizations of lines. This next example we had already done in this video, which is z equals e to the I theta. And again, I wrote down some values for theta going between 0 and 2 pi, and then their values for x and y, using the fact that e to the I theta is equal to cosine theta plus I sine theta, x being the real part, cosine theta, and y being the imaginary part, sine theta. And then what we saw is we went from when x is theta is equal to 0, we started at the point 1, 0. As we progress then, and I'm just going to go for a few points to pi over 2, then we saw that x was 0, y is equal to 1, so we progressed along the curve, and we're progressing in a counterclockwise direction. As we get to pi, we're at negative 1, 0, negative 1, 0, and then at 3 pi over 2, we're at 0, negative 1, and then finally at 2 pi we're at 1, 0. And again, the idea, this was a closed curve because we start where we began, and also this is goes in the counterclockwise as theta progresses. We can look at this related example where z is equal to z naught plus r e to the I theta. So we're going to write z naught as x naught plus I y naught, and then we have r, and then e to the I theta again is equal to cosine theta plus I sine theta, so I can group my real parts, which is x naught r cosine theta, and my imaginary part, which is y naught r, I need an r sine of theta. And from what you know of algebra, you may guess that what this does is it shifts our circle over to z naught, so that the center is now at z naught, and r, of course, increases our radius. But I went ahead and made my table with just a few points. These are the points I actually know. Everything else I have to look up. But here, x is equal to x naught plus r cosine theta, y is equal to y plus r sine theta. Theta is equal to 0, so this becomes 1, so we have x naught r. This becomes 0, so we have y naught, theta pi over 2. So now cosine theta is 0, we have x naught, and y sine is 1 is equal to r at pi. So we're over here. Cosine is equal to negative 1, so we have x naught minus r, and then y naught is 0. And then finally at 2 pi, we come back around. So graphing these at pi equals 0, so along the x-axis, we have x naught plus r, so here's x naught. We're going to add 2 because we're going to just put in r equals 2 just to make it a little easier on us. And then we go up to y naught, so this is our first point. You know we're going to progress in a circle because this is a circle, but at theta at pi over 2, so we're pointing upwards, we're going to get x naught, which is this point, and then we have y naught plus r. R is equal to 2. So we have this point here, So we're progressing from here to here. And then we have pi, so that's along the negative x-axis. We have x naught minus 2, and then we go up to y. So that's this other blue point. So we progress along the circle, and then at 3 pi over 2, so that's pointing in the negative I direction, we have x naught and y naught, and then we subtract 2. So we have this point here, and then finally at 2 pi, we come back around. So as I said, we've essentially shifted the circle, so its center is at z naught, which is x naught, y naught, and its radius now is equal to 2. This next example is z is equal to e to the minus I theta, which I rewrote in terms of sines and cosines, so that's cosine and negative theta plus I sine negative theta. And this problem is related to z equals e to the I theta, so I rewrote that table here. Now I'll draw my table, or make my table for z equals e to the minus I theta. So I have my theta column here, my minus theta column here, cosine of minus theta, sine of minus theta. And this is how, I'm going to explain to you how I think about it, and maybe it'll seem overly complicated. So what I would do is, if this table makes sense to you, don't listen to my explanation. But if it doesn't, I'm going to tell you how I think about it. So when theta is equal to 0, negative theta is equal to 0. So they're the same. So you can read that right off of here. X is going to be equal to 1, y is going to be equal to 0. When I'm at pi over 2, so this is what I think of. When I want negative pi over 2, that means, and the negative sign means I'm going to go in the clockwise direction instead of our normal counterclockwise direction. So negative pi over 2 in the counterclockwise direction is equal to 3 pi over 2. So this is what I have written for negative theta. So if theta is pi over 2, negative theta is this angle here, which is equivalent to 3 pi over 2. So I'm going to look up 3 pi over 2, and I see that x is equal to 0, y is equal to negative 1. So I guess I could have written in this column here that negative theta is equal to negative pi over 2, which is equal to 3 pi over 2, right? So you can either go in the negative direction or you can go in the positive direction. Now when I get to theta equals pi, so if I want negative pi, I come over here in the negative direction, but that's equal to the same thing going in the counterclockwise direction. That's equal to pi. So this is going to be the same. So I read off pi, I get x is equal to negative 1, y is equal to 0. Next I get 3 pi over 2. So if I go here and I graph negative 3 pi over 2, that's the same thing as going in the counterclockwise direction as pi over 2. So again, I could think of this pi over 2 as negative 3 pi over 2 in the clockwise direction, and that's equal to pi over 2 in the counterclockwise direction. So I can read that here, so pi over 2, so I get 0 for x, 1 for y. And then finally at 2 pi, so I've gone all the way around in the negative direction, but that's the same thing as going all the way around in the positive direction. So I'm back where I started. Now if I plot my points, and of course there's a lot of points in between, but I'm just trying to get us, I know it's going to be a circle, so I'm just trying to get a sense of what's happening. So at theta equals 0, I'm at 1, 0. So that'll be this point here. As I progress to theta is pi over 2, I'm going to go from 0, negative 1. So I'm going over this way. And then at theta equals pi, I'm at negative 1, 0. So that brings me over here at theta equals pi. And then I have at 3 pi over 2, I'm at 0, 1. So at 3 pi over 2, I come to 0, 1, and then finally I come back. So what you see is this negative sign has me traversing the circle in the opposite direction, in the clockwise direction. So the thing to note is this z to the e to the minus I theta and z e to the I theta, they contain the same points of the circle. So their path sort of looks the same, but the circle is traversed in opposite directions. This one here is traversed in the clockwise direction. This one here is traversed in the counterclockwise direction. This next example is z equals e to the I 2 theta, which I rewrote using Euler's identity as cosine 2 theta plus I sine 2 theta. And because this problem is related to z equals e to the I theta, I wrote the table here for e to the I theta. Now I'm going to fill in my table for 2 theta. So when theta is equal to 0, 2 theta is 0, so for cosine and sine I get 1, 0. When theta is equal to pi over 4, 2 theta is equal to pi over 2, so for cosine and sine I'm going to get 0, 1. When theta is equal to pi over 2, 2 theta is equal to pi, so for cosine of theta I'm going to get negative 1, 0. And when theta is equal to pi, 2 theta is equal to 2 pi, so I've come all the way back around now to 1, 0. And then just looking at 2 pi, then 2 theta is equal to 4 pi. So kind of what that tells me, I start at theta equals 0, and I'm here at 1, 0. Theta equals pi over 4, I come up to 0, 1. Theta equals pi over 2, and I come over here to negative 1, 0. And as theta is equal to pi, I've come all the way back around. And this is just this much of this table. And if you compare that to the table over here, to go all the way back around to my 1, 0, I had to go 2 pi. So in a sense, I've done this circle twice as fast. And by the time I get to 2 pi, you see that I've come all the way back around again to 4 pi. So I've traversed the circle twice. So I've written that down. My z equals e to the I 2 theta and z equals I theta contain the same points of the circle. But for z equals e to the I 2 theta, and when theta is going between 0 and 2 pi, I traverse the circle twice. This is a review of the 4, actually there's sort of 5, this extra one here, but the 4 main examples we just had. We had examples of lines, so you will want to know how to parameterize lines and the different ways you can do it, like parameterized based on x or t or maybe y. And we had examples of that. You also want to be able to parameterize a circle, such as something of the form z equals e to the I theta. And in fact, we also had a circle centered at z naught with radius r, so you want to be able to parameterize this as well. You want to understand how to reverse the direction of this contour. So here, this is going in the counterclockwise direction. This negative here will give us the clockwise direction. And then also, this multiplying the theta here will give us something that goes around twice as fast. And if it's not apparent from this slide, so the things that are important for you to know how to parameterize are lines and circles. And actually, like so many circles. In the same way that differential equation, oftentimes the solution is of the form e to the at. In complex analysis, there are so many circles and so many integrations have 2 pi in the answer because you're integrating circles. And the reason for that, you will see later in this class that you will have occasion where you want to enclose a point inside a closed curve. So you can go and you can draw sort of a fancy curve, as fancy as you want. This is supposed to be a tree to enclose your curve. But then when it comes down to actually parameterizing your curve, all of a sudden those circles will start to look really good. And if you're not already good at drawing circles, by the end of this class, you'll be really good, or at least much better. So lines and circles, you definitely need to know how to parameterize those. So now we have a couple of other definitions to finish up our content. So this first statement isn't so much a definition as an observation, which is the parametric representation used for any given arc C is not unique. For example, to parameterize the right half of the circle of modulus z equals 2, in other words, the radius 2, in the counterclockwise direction, So it's this curve we're trying to parameterize. We can do that using our exponential form. So the radius is 2e to the I theta, where theta goes between negative pi, and the negative pi and pi is just reflecting that we just want the right half of the circle. The other thing we can do is using modulus of z, which is equal to square root of x squared plus y squared is equal to 2, which means x is equal to the square root of 4 minus y squared. So we can also express z, a parameterization of y, and then x. So this is z of y. So right, our y is our parameter, and then we get our x in terms of y and y, which expresses our square root of 4 minus y squared plus iy. And here again, in this form, we get the relation that x is equal to square root of 4 minus y squared from this term here, which is exactly the relation of modulus z is equal to 2. The other definitions we need are a contour or piecewise smooth arc is an arc consisting of a finite number of smooth arcs joined end to end. So if z of t, when t goes from a to b, represents a contour, z of t is continuous, whereas its derivative, z prime of t, is piecewise continuous. So in other words, here's a simple contour, closed contour. This triangle is another simple closed contour. This triangle is piecewise smooth. In other words, it's basically consists of 3 smooth arcs joined end to end. So 1 arc, 2 arcs, 3 arcs joined end to end. And z of t is continuous, this arc is continuous, however the derivative is piecewise continuous. So it's continuous for each arc. But here at the joining points, because of the sharp points, it's not continuous at these joining points. So that's what this is about, the contour, where you join different arcs together. And then we've already used this part, the simple closed contour. When only the initial and final values of z of t are the same, the contour is a simple closed contour, and examples include the circles, as well as the boundary of a triangle or rectangle taken in a specific direction. The length of the contour or simple closed contour is the sum of the lengths of the smooth arcs that make the contour. Our last definitions, points on any simple closed curve or simple closed contour are boundary points of 2 distinct domains. So these points are the boundary points are of 2 domains. One is the interior C, which I have shaded in green, and it's kind of what you would intuitively call the interior of the curve. And the other is the exterior of C, and is unbounded. So it's unbounded because it goes off forever, and that I have shaded in yellow. To review what we have discussed in this video, we have talked about contours, and contours become important because integrals of complex valued functions of a complex variable are defined on curves in the complex plane rather than just on intervals of the real line. So this is different from our last video where we did integrals and derivatives of complex valued functions of real variables. Now we're looking at complex variables. So we will be looking at classes of curves that are adequate for the study of such integrals. We talked about arcs. There are a set of points in the complex plane for which x equals x of t and y equals y of t, for t going between a and b. And x of t and y of t are continuous functions of the real parameter t. So we talked about what this does is t, we can think of it as time, and then we have a function x of t, which tells us where the x-coordinate is in time, and we have a function y of t, which tells us where the y-coordinate is in time. And from that, as we let t go from whatever some value a to b, we can see the curve that is traced out as time progresses from a to b. We have an alternative notion to describe the points of C, which is z of t is equal to z of t plus x of t plus I y of t. The arc is a simple arc or Jordan arc if it does not cross itself. It's a simple closed curve or Jordan curve when the arc is simple except for the endpoints where the 2 endpoints are the same. Such a curve is positively oriented when it is in the counterclockwise direction. That is the direction of increasing theta when we're talking about angles. The geometric nature of a particular arc often suggests different notations for the parameter t. So sometimes we use x as the parameter, or y can also be the parameter, or theta can be the parameter, as we have in these examples. We did an example of parameterizing lines. Here we have z is equal to, our x function is just x, and our function for y of t is just x, or y of x is just x. Here for this portion of the graph, our function for x is just x, and our function for y is I. And you can see that here we have this line of y equals x, and here we have y equals 1. We also looked at parameterizing a circle, which is z is equal to e to the I theta. And that's a simple closed curve. When theta goes between 0 and 2 pi, you get the complete circle. And also, one of the things about the parameterization, it's important to talk about the limits on t. Here we have z equals e to the minus I theta. And then this minus I gives us the negative, or the opposite direction, so it's a clockwise orientation. And here we have z e to the I 2 theta. And what we said about this is the points are the same, but it gets around twice as fast. So you only need theta to go to pi in order to get around the whole circle. And then last, we have this, when we talked about z equals e to the I theta, that if we have z equals z naught plus r e to the I theta, that will shift the center of our circle to z naught, and then our radius will be equal to this capital R. We have another note and some definitions. The parametric representation used for any given arc C is not unique, and we did an example where we had half of a circle and we parameterized it 2 different ways. We have the definition of a contour, or piecewise smooth arc, is an arc consisting of a finite number of smooth arcs joined end to end, and that z is continuous, whereas the derivative is only piecewise continuous. And when only the initial and final values of z or t are the same, the contour is called a simple closed contour. And examples were the circle or boundaries of a triangle. Then we also talked about the interior of a contour and exterior of a contour, and we showed examples of that. For review, I have these 3 problems for you to try. The first one is to parameterize 3 different curves from 0 to A, and then from A to B, and the last curve is 0 to B. The next one here is to derive the equation of the line through the points alpha A and beta B in the tau t plane. And here it shows a curve, but you want to derive the equation of the line. And last, you want to parameterize this curve, which is half a circle on the lower half of the YZ plane. I suggest you pause the video, give these problems a try, and when you come back, I'll have solutions for you. These are the solutions to the 3 problems. And that's it for this video. Thank you for watching.